We live in an era where technology is obsessed with more. We want our audio louder, our Wi-Fi stronger, and our data streams faster than ever before. To get that extra boost, we rely on amplifiers. These are circuits specifically designed to take a small electrical input and multiply it into a much larger output power. But pouring relentless energy into a system creates a massive problem. When a signal becomes too strong, it distorts audio, blows out speakers, and can completely fry delicate microchips. Raw, unconstrained power is inherently destructive. If you push an electrical system past its physical limits, the hardware simply breaks. The solution to this overload problem is the exact opposite of an amplifier. It is called an attenuator. An attenuator is a circuit intentionally designed to reduce the voltage or power level of an incoming signal. But it has a strict rule to follow. It must weaken the power without ruining the actual shape of the signal itself. Because of this strict rule, an attenuator is not an inefficiency or a flaw in the wiring. It acts as a dedicated safety valve, preserving the exact fidelity of the original data while keeping the hardware perfectly safe. The most common version of this circuit is the resistive attenuator. If you have ever turned down a volume knob, you have used one. Inside, this circuit uses a network of resistors to absorb excess signal power, harmlessly bleeding it off as heat. Standard resistors do not discriminate between different frequencies. They weaken every part of the signal equally, ensuring all the complex peaks and valleys remain perfectly proportional. This setup gives us broad control over the total electrical energy flowing through the system, acting as a primary brake pedal to keep the overall output in check. Sometimes, however, simply dropping the voltage is not enough, especially when you are connecting two entirely different pieces of hardware together. That is where the interface, or matching attenuator, comes in. This specific circuit reduces the voltage level while keeping the output resistance exactly the same. This impedance matching is vital. If a strong signal hits a new piece of hardware with the wrong resistance, part of that signal will violently reflect backward along the wire. By matching the resistance, these attenuators act as crucial translators. They ensure mismatched electronic systems can safely bridge their connection and communicate without causing physical damage. But what if you do not want to weaken the entire signal? What if you only want to target one specific part of it? For that, engineers use frequency-selective attenuators, better known as filters. These are the foundational circuits behind audio-graphic equalizers. On a frequency spectrum chart, a low-pass filter heavily attenuates high frequencies on the right. A high-pass filter does the opposite, blocking lows. Finally, band-pass filters isolate a middle range to transmit, while band-stop filters reject a specific middle slice. Instead of a blunt volume knob, filters give engineers microscopic control. They can carve out unwanted noise and sculpt the exact output required. Attenuators serve as precision control mechanisms of the electrical world. By calculating exactly how much energy to remove, they transform dangerous power into a functional tool. Without this ability to weaken and filter signals, the high voltage flows needed to move data across a network would overwhelm every local receiver, turning clear communication into a mess of heat and distorted noise. While amplifiers provide the force to push data across the world, attenuators provide the necessary restraint to ensure that signal arrives with its integrity intact.